Campi Flegrei has become one of the clearest examples on Earth of a volcanic system that can deform, shake, and intensify without behaving like a simple magma injection problem. The caldera is the largest active volcanic caldera in Europe and sits beneath a densely populated part of the Naples region, where more than 350,000 people live over a structure that has repeatedly risen and fallen through history. Since 2005, the ground has been inflating again, seismicity has increased, and gas emissions have strengthened. Recent work on the Unrest period from 2000 to late 2023 found a parabolic rise in uplift and a super-exponential increase in the number of earthquakes and seismic energy release, while another study reported that the recent uplift rate reached up to 2 centimeters per month. These are not subtle signs. They are the measurements of a system under sustained stress, but not necessarily a system fed by a brand new shallow magma intrusion. That distinction matters. Campi Flegrei is not a volcano that has behaved the same way in every Unrest episode. In the 1950 to 1953, 1969 to 1972, and 1982 to 1984 crises, the caldera rose by roughly 0.75 meters, 1.70 meters, and 1.85 meters, respectively, with the last episode forcing evacuations and leaving Pozzuoli's harbor too shallow for normal use. The current phase began in 2005, but the deformation pattern, the seismic cadence, and the gas-driven behavior are not identical to the 1980s. In fact, the recent literature repeatedly emphasizes that the system has become more complex, not simply more intense. That complexity is exactly why the phrase "it's not magma" is both useful and incomplete. The present uplift is increasingly being explained by overpressure in fluids, by sealing and reopening of the crust, and by the mechanical response of weakened rock, rather than by a straightforward upward push from a fresh, shallow melt body alone. A major shift in interpretation began years ago and has not gone away. A 2018 INGV interpretation, built on more than 37 years of geochemical and geophysical data, argued that the ongoing bradyseism since about 2005 was not caused by new magma intruding into the shallow crust. Instead, it described an inflow and outflow of magmatic gases through the Phlegreian aquifers, with the deeper reservoir located at roughly 8 kilometers depth supplying the heat and volatiles that altered the groundwater system. In that model, the uplift is linked to drying and pressurization of the aquifers, not to a shallow melt lens forcing its way upward. That is a very different mechanism from the older intuition that ground up equals magma up. It does not remove magma from the system. It relocates magma to the deeper source of heat and gas, while the actual driver of uplift is the pressurized hydrothermal domain above it. The scientific review published in 2021 sharpened that argument. It described Campi Flegrei bradyseism as a cyclic magmatic hydrothermal process tied to structural and lithological heterogeneity, with variable permeability that changes horizontally and vertically across the caldera. That review said the available data are inconsistent with a model in which the unrest is driven exclusively by shallow magmatic intrusions. It also highlighted an impermeable shallow layer, the so-called B layer, acting as a cap above an anticlinal structure beneath Pozzuoli. In practical terms, that means the system can behave like a sealed pressure vessel. Fluids enter, pressure rises, the lid deforms, and seismicity follows. The key point is that the uplift can be produced by fluid pressure and rock sealing even when magma is not physically forcing its way into the uppermost crust. That is why the debate at Campi Flegrei has gradually moved from "is magma rising" to how are fluids, heat, fractures, and rock strength interacting. Recent imaging has made that interaction harder to dismiss. A 2025 Nature Communications study combined high-resolution three-dimensional P-wave and S-wave seismic images with rock physics experiments and identified a gas-rich reservoir below about 2 kilometers depth, a deformed caprock between roughly 1 and 2 kilometers, and basement below 3.5 kilometers. The study found that seismicity migrates downward from the caprock and that stress changes activate deeper events along inner caldera boundary faults. Its central result is direct. The reservoir aligns with the area of maximum uplift, and the deformation acceleration is consistent with poor fluid pressure, as confirmed by laboratory experiments on site-relevant rock. In that framework, the ground rises because a pressurized gas reservoir pushes against a mechanically weakened seal. The source of the pressure is still tied to the volcanic system, but the immediate cause of uplift is fluid pressure within a confined structure rather than a shallow pocket of mobile magma. That is one reason the recent Stanford-led study drew so much attention. It framed the Campi Flegrei unrest as a geothermal reservoir problem. Earthquakes and land deformation were driven by pressure buildup in a capped reservoir, and the caprock's self-sealing properties help keep the system closed. The study's summary said that pressure from water and vapor in the reservoir can produce seismicity when the lid seals, and that reducing groundwater input or managing water flow could, in principle, reduce pressure in the system. The same work argued that the recurrence of an overpressured reservoir helped drive both the 1980s crisis and the current unrest. It also challenged the older assumption that the main process must be magma or magmatic gas rising into shallower levels. That does not mean water alone explains the whole volcano. It means the mechanical trigger for uplift may be the fluid pressure in the hydrothermal system, with rainfall, permeability, and sealing processes helping determine how fast the system inflates. The reservoir itself is not an abstract concept. Campi Flegrei sits inside a hydrothermal framework that repeatedly stores and releases fluids. The Stanford study described the caprock as fibrous and self-healing, meaning cracks can be sealed by mineral growth under hot fluid conditions. It also noted that recent surface deformation and seismicity can be read together as an expanding pressure field, not as isolated signals. That is consistent with earlier work showing that the caldera's uplift and earthquake rates are tightly linked over time, with the deformation rate and seismicity reinforcing one another during the ongoing unrest. At Campi Flegrei, the crust is not simply lifting because something is forcing a rigid dome upward from below. The crust is responding because the lid, the reservoir, and the fault network are mechanically coupled. That coupling makes the system far more sensitive to pressure changes than a single-source magma model would suggest. A newer AGU Advances paper published in 2025 adds another layer to the picture. It identified a weak tuff layer at roughly 2.5 to 3.0 kilometers depth, likely capable of trapping magmatic fluids. The study argued that past magmatic intrusions may have arrested at the limestone to tuff transition, where they heated, damaged, and altered surrounding rocks. In that scenario, the uplift is not caused by a fresh batch of magma pushing directly into the shallowest crust. Instead, the legacy of older intrusion episodes has left behind a mechanically weakened horizon that can retain hot pressurized fluids, building overpressure and deformation. The paper's wording is important. Past magmatic activity may have created the weakened architecture that now governs the present unrest. That means the current uplift can still be volcanic in origin without being the direct expression of a new shallow magma body. The volcano's past is helping control its present. That interpretation fits the broader evolution of Campi Flegrei studies over the past several years. Work published in 2024 found that the caldera's upper crust has been deforming and seismicity has been accelerating over the 2000 to 2023 interval, with a close temporal correlation between uplift rate and earthquake rate. The recent data also suggest a progressive mechanical weakening of the upper crust, which is exactly what one would expect in a system where repeated inflation, cracking, fluid recharge, and sealing have been happening for years. When a system shows parabolic uplift, rising earthquake counts, and increasingly sensitive deformation seismicity coupling, the right question is not simply whether magma is present deep below. The better question is how much of the observed motion is being transferred through fluid pressure, caprock sealing, and stress accumulation in damaged rock. Campi Flegrei appears to be answering that question with a hydrothermal structural mechanism that remains linked to magma at depth but is not reducible to a fresh, shallow intrusion. There is also a practical reason the distinction matters. If the immediate driver is fluid pressure in a capped reservoir, and a damaged upper crust, then changes in permeability, groundwater recharge, venting, and sealing become central to how the unrest evolves. That does not make the hazard smaller. A pressurized hydrothermal system can fracture rock, trigger swarms, and generate phreatic explosions without a new magma body reaching the surface. The 2025 Nature Communications study explicitly said that seismic activity and the possibility of a phreatic explosion should be considered plausible scenarios. This is why the recent literature does not read as reassurance. It reads as refinement. Campi Flegrei is not behaving like a simple magmatic chimney. It is behaving like a layered, pressurized, mechanically evolving volcanic hydrothermal machine whose upper crust has been weakened by older events and is now responding to renewed overpressure. The behavior now unfolding beneath Campi Flegrei has become increasingly difficult to explain using older eruption models that focused almost entirely on ascending magma. The caldera is still volcanic, still dangerous, and still thermally connected to deeper magmatic reservoirs, but the strongest signals emerging from recent studies point towards something more structurally intricate. Pressure appears to be accumulating within a hydrothermal system that has become progressively sealed, mechanically weakened, and highly responsive to stress changes. That distinction changes how the current unrest is interpreted because it means the surface deformation can accelerate even when molten rock is not directly intruding into the shallow crust. One of the clearest indicators of this evolving behavior is the way seismicity has changed alongside uplift. Since the current unrest phase intensified, earthquake swarms have not only become more frequent, they have also migrated through different portions of the crust in patterns that match fluid movement and stress transfer. Researchers examining the distribution of earthquakes beneath Pozzuoli identified clusters concentrated around structurally weakened zones and fault intersections, especially near the caprock above the pressurized reservoir. The earthquakes increasingly resemble a crust responding to overpressure and fracture propagation, rather than a crust simply being displaced by a rising magma chamber. This is a crucial distinction because magma intrusions tend to produce more coherent migration pathways and sharper deformation signatures. At Campi Flegrei, however, the deformation field is broader and more mechanically diffuse. Surface uplift has spread across the central caldera, with repeated inflation cycles affecting multiple sectors simultaneously. INSAR satellite measurements and GNSS ground stations have shown that deformation rates accelerate and decelerate in close synchronization with seismic swarms, implying that pressure pulses are moving through interconnected fracture systems. Those pressure pulses are increasingly interpreted as fluids and gases exploiting zones of weakness in the crust. The gas itself provides another important clue. Campi Flegrei has long emitted large quantities of carbon dioxide and water vapor through fumaroles around Solfatara and Pisciarelli. Over the past 2 decades, gas chemistry has shifted towards stronger magmatic signatures, including increases in carbon dioxide relative to hydrothermal components. Yet even this evidence does not necessarily require shallow magma ascent. Deep magma degassing can inject large amounts of volatile-rich gases into the hydrothermal system without magma physically rising into the upper crust. Once those gases enter confined aquifers and porous rock layers, they can dramatically increase pressure, reduce rock strength, and intensify deformation. The Pisciarelli fumarole field has become especially important because it appears to be acting as a surface release valve for deeper pressure accumulation. Temperatures in the fumarolic area have risen substantially during the current unrest period, and emissions have become increasingly vigorous. Satellite thermal imaging and field measurements indicate that the hydrothermal system beneath Pisciarelli has been repeatedly recharged by hot fluids ascending from depth. The process resembles a pressurized circulation network more than a single vertical magma conduit. Hot gases rise, interact with groundwater, accumulate beneath low permeability layers, fracture surrounding rock, and periodically vent through fumaroles and fault systems. This interaction between fluids and rock is central to understanding why Campi Flegrei continues deforming year after year. The upper crust beneath the caldera is composed of volcanic tuffs, altered ash deposits, fractured lava units, and sedimentary sequences that respond differently under stress. Some layers behave elastically, flexing under pressure before relaxing. Others behave plastically, deforming permanently after repeated stress cycles. Hydrothermal alteration weakens many of these rocks further by chemically transforming minerals and increasing porosity. Over time, repeated pressurization reduces the crust's ability to resist deformation. The structural architecture of the caldera amplifies this behavior. Campi Flegrei is not a uniform volcanic basin. It contains nested collapse structures, buried faults, ring fractures, and caldera boundaries formed during massive eruptions thousands of years ago. These inherited structures strongly influence where stress accumulates and where fluids migrate. Seismic tomography has revealed that many recent earthquakes align along pre-existing weaknesses rather than forming entirely new pathways. This means the present unrest is partly controlled by geological scars left behind by ancient eruptions. One of the most important of those ancient events was the Campanian ignimbrite eruption approximately 39,000 years ago. That eruption expelled enormous volumes of material and reshaped the regional crustal structure beneath the Naples area. Later eruptions, including the Neapolitan Yellow Tuff event around 15,000 years ago, further modified the caldera's architecture. The current hydrothermal system exists within the fractured remnants of those catastrophic eruptions. Every new episode of uplift and seismicity interacts with structures inherited from those earlier collapses. This inherited complexity may also explain why deformation sources inferred from geodetic data often appear shallow despite the deeper origin of heat and volatiles. Pressure can propagate upward through fracture networks and become trapped beneath impermeable horizons only 1 to 2 miles below the surface, roughly 1.6 to 3.2 kilometers. The result is a shallow deformation signal produced indirectly by deeper volcanic processes. In other words, the crust deforms where fluids accumulate, not necessarily where magma resides. Another important development has been the increasing recognition of mechanical weakening within the caldera. Several recent studies argue that repeated uplift cycles have brought portions of the crust closer to failure conditions. This does not automatically mean eruption is imminent, but it does mean smaller pressure increases may now produce stronger seismic responses than in previous decades. Earthquakes occurring during the current unrest have occasionally reached magnitudes above 4, large enough to damage buildings and alarm residents around Pozzuoli and western Naples. The growing sensitivity of the crust is especially concerning because it introduces nonlinearity into the system. A small increase in fluid pressure may produce disproportionately large deformation or seismic responses once rock strength declines past certain thresholds. Researchers have compared this behavior to material fatigue in engineering structures. Repeated stress does not always produce immediate failure, but it progressively weakens the material until even moderate loading becomes disruptive. Campi Flegrei may now be approaching that kind of mechanically sensitive state. At the same time, the caldera's behavior continues to resist simple forecasting. Historical unrest episodes did not always culminate in eruption. The 1982 to 1984 crisis produced intense uplift and thousands of earthquakes, yet no eruption followed. The present unrest has already lasted longer than that earlier episode, with cumulative uplift now exceeding 13 feet or roughly 4 meters in parts of Pozzuoli since the early 1950s. Despite that enormous deformation, magma has not erupted at the surface. This persistence is precisely why the hydrothermal interpretation has become more compelling. A magma-driven eruption model alone struggles to explain decades of repeated uplift without eruption. A fluid pressure model, however, allows for prolonged unrest cycles in which gases and hydrothermal fluids repeatedly accumulate and dissipate without requiring magma to breach the surface. The system can remain hazardous and unstable while still operating below eruptive thresholds. Yet the distinction between hydrothermal unrest and magmatic unrest should not be misunderstood as a separation between two unrelated systems. The hydrothermal system ultimately depends on deep magmatic heat. Without magma degassing at depth, the pressure source would weaken over time. Campi Flegrei therefore remains fundamentally volcanic, even if shallow magma intrusion is not currently the dominant mechanism behind the uplift. Deep magmatic fluids continue feeding the reservoir, heating groundwater, and driving gas emissions. Recent models increasingly describe the caldera as a coupled magmatic hydrothermal system rather than treating magma and fluids separately. In these models, magma supplies heat and volatiles from deeper reservoirs, while hydrothermal circulation redistributes energy through the upper crust. Surface deformation emerges from the interaction between those layers, rather than from one isolated source. That framework better explains the observed combination of uplift, fumarolic intensification, seismic swarms, and caprock deformation. The strongest takeaway from the published work is therefore not that magma is absent, but that magma is not the immediate explanation for the rising ground. Deep magmatic heat and gases still matter, past intrusions still matter, and the caldera's structure still matters. But the lifting itself is increasingly being tied to a gas-rich reservoir, a sealing caprock, a weak tuff layer, and a hydrothermal system that stores pressure until the crust deforms or breaks. That is a more complicated and in many ways more realistic reading of Campi Flegrei's present state. It is also the reading that best matches the combined evidence from seismic imaging, rock physics, geochemistry, and deformation records now available. The ground is rising because the system beneath it is being pressurized through fluid-rich pathways and mechanically weakened horizons, with magma acting more as the deep engine of heat and volatiles than as the direct shallow piston.